Hi everyone. Okay, because some of you were unable to come to the lunchtime revision session today, I'm happy to go through these questions again, recorded. I think it's important to go through all of these questions because they were answered poorly by the state. Okay, the first question, and these slides are on Edmodo under lunchtime revision session. Okay, so for the first question, we have CH4 plus water produces carbon monoxide and hydrogen gas. Here we have the production of carbon monoxide and basically a concentration versus time graph. And you can see that carbon monoxide at time 0 had a 0 concentration. Concentration of carbon monoxide was 0. Okay, but CH4, the concentration of CH4 at time 0 was something up here, and then it decreased over time. So this tells me CH4 decreased by 1 unit until we reached equilibrium. So here we reach equilibrium, and CO increased by 1 unit, telling me that initially there was no CO. Okay, so the question asks, on the graph above, draw a line to show the change in concentration of hydrogen gas as the reaction progresses. So if there was no CO at equilibrium, if there was no CO in the beginning, we can make an assumption that, well, the production of CO, there was no H2 in the beginning either. Okay, because the question asks, so it's not an assumption because the question asks, some methane and steam are placed in a closed container and allowed to react. Okay, so there was no H2O at the beginning, so H2 at the beginning, so H2 will start here. And where will it end? So the production of 1 unit of CO, if we produce 1 unit of CO, we will produce 3 units of H2. It has to reach equilibrium at the same time, so at equilibrium its concentration will be up here. Okay, now we can't, basically, the way you have to think of it is, per a given unit of time, we have to produce 3 times the amount of H2 than CO. So we'll produce a higher concentration in a shorter amount of time. Okay, so it can be something like this. Okay, so this would be the line you would reproduce. Now, the second one says, on the graph above, draw a line to show the formation of carbon monoxide, how it would differ over time in the presence of catalyst. So here we have the formation of 1 unit of carbon monoxide. Because its concentration, catalyst does not do anything to the concentration. Okay, so it only increases the rate at which it's produced, the amount produced in a given time. So we should end up with something like this. Okay, now something that you should think about is, if this actually, instead of catalyst, actually said temp and this said volume, okay, the volume of CO being a gas would be higher. So it would be faster because of temp, and it would also be higher because, well, in this case, because it's an equilibrium question, as temp increases, it's an endothermic reaction, so the concentration of CO would also increase, so we would get something faster but higher as well. Okay, so this question was performed particularly, I think this part was performed well by the state, but let's move on to part B. Okay, so B says, a great deal of care must be taken when handling carbon monoxide, as it's a highly poisonous gas. Even at low concentration, it competes very successfully with oxygen. for hemoglobin. So we have two reactions. We have hemoglobin and oxygen, and we have hemoglobin and carbon monoxide. Okay, and then we have a particular K. Now, because it says it competes very successfully, so it means it's winning the competition. So in other words, we will have quite a bit more of this carbon monoxide bond to hemoglobin. So more of this and less of this. So it really means that K2 is greater. The K that relates hemoglobin to carbon monoxide has a higher value than the K that relates oxygen to hemoglobin. So that kind of answers question 1. What does the above information indicate about the magnitude of the equilibrium K1 compared to K2? I would say K1 is less than K2. Okay, and if you want to see their answer, and 76% of that state, the state got it right. Okay, so it wasn't a particularly difficult question, but they basically said K1 is smaller than K2, okay, which is pretty much what we said, or K1 is less than K2, or K2 is greater than K1. So they even accepted the little arrows showing that. Okay, for the next one, it says, the rates of a chemical reaction may be explained by using the collision theory model. Indicate whether the following statements are true or false. Endothermic reactions are always slower. Well, that's false, because at equilibrium, the reaction of the endo, whether that be the forward or the reverse, equals the reaction, the rate of the endo equals rate of the exo. Okay? Part 2. All particles have the same kinetic energy at a fixed temperature. Okay, so kinetic energy, by definition, is a half mv squared. So we know it's mass times velocity. Now, the speed changes as particles bump into each other. But not only that, particles are different masses, so it will be false. But not only that, you guys know that because of your Maxwell-Boltzmann distribution, which relates kinetic energy to number of particles. So you should know from this that there are actually a whole range, and this would be activation energy, there are actually a whole range of particles with different kinetic energies at a given temperature. Because remember, we could do this for 60 degrees, then if we do it at 180 degrees, we have something that's a little bit more spread out like that. Okay. So, reactant particles need to collide with sufficient energy to react. Well, that makes sense. The rate of a reaction at a constant temperature increases as the reaction proceeds. No, the rate of reaction decreases because at first there is the highest concentration of reactants or of products, whatever you're adding in. But over time, as you're converting these into products, the rate of reaction decreases. So it decreases over time because you have a less particles, less chance of collision, and therefore less number of successful collisions per time. Okay, part 5. Increasing the temperature increases the fraction of collisions with energy above the activation energy. So fraction or proportion, same thing, and this is true. Okay. Question 6. Oops. Okay, dinitrogen tetroxide is a colorless gas. And this is a brown gas. The concentration of this can be determined using a spectrophotometer. The equation for the reaction is this. Okay, write an expression for the equilibrium constant for the reaction. I'm going to do this very quickly because we should all know how to do this by now. Okay. Question asks, some pure NO2 is placed in a gas syringe at 25 degrees Celsius, okay, and allowed to reach equilibrium. Keeping the volume constant, the temperature is raised to 35 degrees Celsius, increase in temperature. The brown color then becomes more intense, okay, increasing temperature, shift to the right, okay. Increasing temperature results in a shift to the right. Okay, so that's just writing down the facts. Now, how would we answer that question? We would say something in terms of Le Chatelier's principle. Okay, as there is an increase in temp, the system partially opposes this change by decreasing the temp by absorbing the excess energy by favoring the forward endothermic reaction, increasing the concentration of products and increasing K. Okay, part 2. Keeping the temperature 35 degrees, the plunger is then pushed in so as to halve the volume. Okay, so let's draw this out. Okay, let's say we've got N2O4, NO2. Now, if the volume is halved, immediately the concentrations increase. And what is affected more by it? The NO2 is affected more by it. But anyway, the concentrations increase, and then it will want to reduce. So this increases the pressure. Increase in pressure. So this is when volume is halved. Okay, increases the pressure. It wants to decrease the pressure by moving to the side with the least number of particles. So it favors the reverse reaction, and in other words, increasing N2O4 and decreasing NO2. But remember, it's just partially opposing this change. So we will never actually get, this was where the original equilibrium was. We'll never actually get the concentration of NO2 to be less than it was at the original equilibrium. So in answering this question, which states, is the brown mixture more or less intense when the volume was halved, okay, than in the original mixture? It's actually more intense. It would be less intense than when we initially halved it, but it's more intense than the original equilibrium. So you would say more intense. Then you would say than the original equilibrium. Okay, so it'd be more intense than the original equilibrium, but it does decrease according to Le Chatelier's principle. But remember, Le Chatelier's principle is partially opposing the change. Think about it as a temperature in temperature. For example, you decrease the temperature to 60 degrees from 100 degrees. Le Chateliers would say that you want to increase again, but it's never going to get back up to 100 degrees, nowhere near it. Okay, so just try and think of it like that. Okay, so next one. Now, making sure that it's focused. Alright. Give the numerical value at 25 degrees for the equilibrium constant for this reaction. Where we know that at 25 degrees, the equilibrium constant for this reaction is 5.5 times 10 to the negative 3, and we have N2O4 being converted into 2NO2. Now, in this case, what have we done? So K equals this for this reaction. Okay, now we've actually flipped it. So K of the forward equals 1 over K of the reverse. Whoops. Okay, equals 1 over 5.5 times 10 to the negative 3. Okay, 1 over 181.81. Okay, now K of the so we haven't only flipped it, so we've actually halved it. So K of the halved is the square root of K of the full. So the square root of 181 is 13.5 or 13.48. So yeah, so 13.5. Now if we want it, we need to also have a unit. So we would have n to the power of a half divided by m. So in other words, m to the power of 1. And we do a half minus 1 is negative a half. So m to the negative 1 half. Okay, so, but it basically says give the numerical value, so we don't really need to have the units, but that's how you work out the units anyway. Okay, question 3. Now this one proved challenging for a few students, so let's go through it. Okay, oops. So dimethyl ether is used as an environmentally friendly repellent in spray cans. It can be synthesized from this reaction. Write an equilibrium constant for K. Well, K equals H2O CH3OCH3 divided by CH3OH squared. Calculate K at 350 degrees for this reaction. Now, K equals, we have reversed it, so it is 1 over 5.74 equals 0.174. Okay, and K would be in no units because it's m squared over m squared. Okay, next one. Calculate the concentration of methanol at equilibrium. It tells you methanol is pumped into, and I'm going to write out the reaction so you can use it later. Okay, so it says, and K. Okay, calculate the concentration in moles per litre of methanol at equilibrium. Okay, so at equilibrium, the concentration of methanol equals C equals N over V equals 0.340 divided by 20 equals 0.017 170 M. Now it says calculate the amount in mole of dimethyl ether present at equilibrium. Okay, so the way we can do that is, well, we can't use stoic because stoic, a few people ask, why can't we just do this divided by 2? Because it's not actually saying that this is the initial and it totally reacts. We need to in fact use K. So we know that K equals 5.74 and the concentration of this will be the same as this because it's saying that this is introduced into an empty vessel. So for every part that breaks down, 2 parts that break down, it will make 1 part this and 1 part this. Okay, so in other words, it is our dimethyl ether squared divided by our concentration of methanol, which we've just worked out. So 0.017 squared. Okay, now let's work it out. 5.74 times 0.017 squared. Okay, and then we can just do the square root of that. And the concentration of our dimethyl ether equals 0.0407 M. Now, calculate the amount in mole of methanol initially pumped into the reaction vessel. There's a couple of things that you need to keep in mind, okay, to answer this question. So, the amount of methanol, the way I do it is through a table. So I write out the reaction, so I remember it. CH3O CH3 plus H2O, and then I write out initial concentration, and then I write out initial mole, used mole, equilibrium mole, and then usually because we're given equilibrium concentration we have to work with that. Okay, but here we know that the mole, it says calculate the amount of dimethyl ether present in mole. Alright, so obviously worked it out in concentration. So I actually have to times it by 20. So the amount in mole, this was just times by 20 because we have C, so N equals CV, 0.815 mole. Sorry about that, guys. Okay, so if I work it out, the amount in mole of dimethyl ether present at equilibrium is 0.815 mole. The amount of mole in methanol present at equilibrium is 0.340 mole. Then you have to find out how much of this. Then you have to find out how much of this 0.34 mole was actually used. How much of this was actually required to make 8.15 mole, and you use stoic for that. So the mole of CH3OH required, so in other words used, equals, and you just go by the ratio, 2/1 unknown over known times CH3OCH3 equals 2 times 0.815. So in other words, it was 1.629 mole. Okay? Now initially, the number of moles initially has to be equals used plus equilibrium, would be initial, equals 1.629 plus 0.34. 1.97 mole. Okay, so the answer is, and I would have put that in my question, that it is 1.97 mole. The N of CH3OH initial. Okay, next one. So this question's a little tricky. Now, in solution, pale yellow coloured iron and colourless. So this is yellow, this is colourless, are allowed to form an equilibrium mixture. Delta H is neg. Okay, student investigates this reaction. Complete the following table. We're basically looking at the intensity of the red colour of the solution and also the concentration of Fe3+. Okay, so basically we have to look at each one individually. Okay, so 1 drop of concentrated solution of Ag plus is added, which forms an AgSCN precipitate. So basically we're forming a precipitate out of these. So in other words, we are removing, so one is just basically saying we're removing SCN. So if you remove, SCN, what happens is you'll form a net back reaction, and the color at equilibrium, okay, so it will be less red because you are using some of it to produce more SCN, so less red, or to produce more reactants. Okay, so then it says the concentration of Fe3+ at equilibrium. Well, because you have shifted it to the left, you actually have an increased concentration. Okay, so next one, a drop of concentrated solution of Fe3+ is added. So you increase the concentration of Fe3+. What happens is then you shift to the right and we have an increased color of red, more red. Okay, but then have a look. The concentration at new equilibrium compared to initial equilibrium. So let's draw it out. Let's say that this is Fe. Now we increase the concentration, and then over time it will decrease, because we want to get more of this product to bring Q back to K. But it'll never reach, because remember, Le Chatelier's is partially oppose the change. So it will never actually reach the initial equilibrium. It'll still be higher. Okay? Now the next one. 1 drop of concentrated solution of HPO4 is added, which forms the colourless Fe. Okay, so basically it is reacting with Fe. So in other words, it's saying reducing Fe 3+, and then it will go a net back reaction, and we will get something that's less red because we're removing some of our products to make more reactants, and we will get a concentration of Fe at equilibrium, which will be lower. Okay, lower because we're trying to make more, but some of it's just partially opposing. So Fe here. We remove some of it, and then we increase, but we only partially oppose the change. So at the new equilibrium, it'll still be lower. Addition of a large volume of water. So we add water. Okay. So what happens to the concentrations? Well, let's just look at Fe. We dilute it, so we reduce the concentration, and then it wants to move to the side with more particles. So it'll actually move to the left-hand side, increasing Fe. But again, it's only partially opposing the change, so it'll still be reduced. Okay, and because it goes backwards, we lose some of the red, so it'll actually be less red again. Alright, final question. This reaction is exothermic. Okay, it tells us here. The graph below represents the initial concentrations at equilibrium. Okay, sketch the changes expected to occur if the temperature is increased to a new value. Okay, so 62% of the state got this question right. Okay, so to a new value, so it's increased, and for exothermic that results in a net back reaction. So in other words, we'll increase the concentration of our reactants and decrease the concentration of our product. So let's just do our product, FeSCN. So we reduce that. New equilibrium. In other words, here's the new equilibrium. Okay, and then we'll increase the concentration of Fe and SCN. So here, increase, and here, increase. Now notice that with temperature, like as opposed to if we've got reducing volume or increasing concentration, where it's a sudden change at, instantaneous, the timing is instantaneous. Temperature is a very gradual change because you're really not changing Q straight away. What you're doing is you're increasing the temperature and then that changes K, so it has to catch up. There's no sudden change in concentration. Now just to note, you didn't actually have to get them to cross over, you just had to do these two going up and that one going down. Okay, so I hope that made sense, and let me know if you have any other areas of concern that you want me to cover.